Where's the rest?
Oh, what's going on? We don't have a projector today? There's only one. I'm gonna have to climb up there again. See, we can oh, let's see. It says it's in standby.
Sorry, it was going.
Oh, then that's. Not exactly sure. Okay, good. So let's get started. Thank you for your assignment number 3s. Probably at some point this weekend, I will probably post assignment number 4. It'll be at least partially about like the error propagation stuff that we've been doing recently. Okay, so what we talked about on Wednesday was like this derivation of a result that we all know, right? We all know how to calculate the average of a set of n measurements, but we kind of placed it on a firm foundation where we use the Gaussian distribution and this idea of maximum likelihood. So, oh, fuck off. No. Okay, I'm gonna have to follow this. No way. Should I just tell it that I have the filters?
Say please and thank you. Lie. They'll lie. Always lie.
Okay, so the idea was we made a set of n measurements, x1 to xn, and we're going to assume that we make those measurements by doing the same experiment over and over and over again. And so if we do the same experiment, then all the uncertainties in each of the measurements should, of course, be equal. So what we did then is said, okay, let's imagine that these data follow a Gaussian distribution. then I could ask the question, what is the probability that I would measure x1 with my first measurement, and then x2 with the second, and x3 with the third, and so on? Ended up being this product of a bunch of individual Gaussian distributions, which had some prefactor, which was constant. And then there was, a product of exponentials is the same thing as an exponential of a sum. And that exponential had the individual measurements minus the mean. And our goal was to try to find an expression for this mean. The way we did it is we said, let's assume that the data set that we do measure ends up being the data set that has the highest probability of being measured. It's the most likely data set. So our strategy was to maximize this probability. The way we did it is we minimized everything inside the exponential, without that negative sign. And when we did that, so there we go, the minimization of this quantity was called the method of maximum likelihood, and we found that the mean was given by the expected expression. And then we did propagation of errors to find that the uncertainty in the mean is given by the standard deviation divided by the square root of the number of trials. Mu would be like so we had this idea of like parent distributions and sample distributions, so we could never actually know the parent distribution, but mu would be the mean of that true parent distribution. Like if we could take an infinite number of measurements, then this mu prime would converge towards. Yeah. Okay, good. So what I want to do today is I want to follow the same sort of argument, but we'll put like a little twist on it, okay? So what we're going to talk about today is the weighted mean. So what I want to imagine is that now we have a set of values. Again, it would be x1, x2, up to xn. But this time, each of the individual values has a different uncertainty. So how could that be? We have a couple of examples from the lab. So in black body, what you do is you measure Planck's constant. You actually get 4 different values because we measure Planck's constants for 4 different wavelengths. And so the analysis is the same, but because they're all at different wavelengths, the uncertainties you get out at the end will be a little bit different. Or if you do Boltzmann's constant, you measure Boltzmann's constant by taking some voltage and current measurements from a transistor when the transistor is at 3 different temperatures. And so you can get these 3 values of Boltzmann's constant. They all have different uncertainties because the temperature of your apparatus is different in 3 cases. So how should we combine measurements of the same quantity, but when those measurements all have different uncertainties? Okay, so that's really what we want to think about. So maybe let's write it that way. How should we combine different measurements, say x1, x2, and so on to xn, when each measurement has a different uncertainty. So we'll call the different uncertainties sigma 1, sigma 2, up to sigma n. Okay, and so that's the question. I guess we should write down an example in Phys 232 lab. We measure Boltzmann's constant at 3 different temperatures and find, let's say, KB1 plus or minus sigma 1, KB2 plus or minus sigma 2, and KB3 plus or minus sigma 3. And so the question really is, what is the appropriate value of, let's say, KB average to report? And more than that, what is the final uncertainty in Boltzmann's constant? Hey, I think we probably have some intuition about what we expect from our result. Would you expect, if KB1 has a small uncertainty compared to sigma 2 and sigma 3, should the average be closer or further away from KB1 compared to the others? Right, if we have a small uncertainty, we kind of think that, look, that was our best measurement, so how should that affect our average? The average should be closer to that value of KB1, right? And it, there sometimes could be like physical reasons why we would expect that. In Boltzmann's constant, if this is the room temperature measurement, the transistor is attached to a big chunk of brass designed to keep its temperature stable during the whole experiment. Whereas when we do the ice water and boiling water, there could be significantly more drift and fluctuations in the temperature. And so there might be a good reason for this uncertainty to be small compared to the other two. And if it is small, this measurement should have more weight when calculating the average compared to the others. Okay, so maybe we could just make that sort of observation. We expect measurements with small uncertainties to be, to be more important when determining the average. Okay, well, our approach is going to be more or less the same as the approach we used for the normal mean that we did last time. So again, the approach is to use the method of maximum likelihood and we want to, well, okay, so we're gonna maximize this P of mu prime. Okay, so let's do that. So let's say we're gonna have, just to write it down again, we'll do a general example, x1 plus or minus sigma 1, x2 plus or minus sigma 2, up to xn plus or minus sigma n. So if you want to, you could think of these as Boltzmann constant measurements or something like that. Okay, well, the probability of measuring the first value, x1, is given by this Gaussian distribution, which was, well, it was 1 over root 2 pi, and then there was a sigma. So now here's where we're going to be a little bit more careful. Now this value of sigma will change for the different measurements. So this is going to be now a sigma 1, and then there was an exponential of minus 1/2 of, let's see, it would be x1 minus mu prime divided by, previously we would just put sigma here because they'd be the same for every measurement, but now we're allowing the possibility that each measurement has a unique value of sigma, and so then we have to square it like so. And so then P of mu prime is going to be equal to this product from I equals 1 to n of Pi. And that product is going to be, well, on Wednesday, we just said, if I take a product of n terms, my prefactor is the same for every single factor. And so we just got this prefactor raised to the power n. That's not quite true anymore, because instead of sigma times sigma times sigma times sigma n times, we have sigma 1 times sigma 2 times sigma 3 times sigma 4 and so on. So we have to write this prefactor as, we just have to write it as a straight product. So this would be I equals 1 to n of 1 over root 2 pi sigma I. And so that's going to be our prefactor. It will again turn out like this part of it is not going to be interesting. In fact, I did it again, didn't I? Last time someone reminded me that I left out my dx's, and so I need my dx. Okay, so there's our dx's. But still, we're not going to care about this because we're going to do a minimization with respect to mu prime, and there's no mu prime in here. So we could just emphasize that this is constant with respect to mu prime. Okay, but then we're still going to have a product of n exponentials, which we can write as the exponential of a sum minus 1/2 sum I equals 1 to n. This looks more or less the same, except for the fact that we have a sigma I in the denominator. And so it should look something like that. Okay, so to maximize P of mu prime, we will minimize this following factor. We called this factor, okay, we called it x last time, so I guess I'll stick with x. X was equal to 1/2 the sum of I equals 1 to n of xi minus mu prime over sigma I all squared. Okay, so we're going to minimize x with respect to mu prime. Okay, and let's see what happens when we do this. On Wednesday, we would have just factored out the sigma squared because it would be the same for every term in the sum, but we can't do that this time. Okay, so dx d mu prime is going to be 1/2 sum of I equals 1 to n of d by d mu prime of xi minus mu prime over sigma I squared. Okay, so let's see, and then we will eventually want all of that to be equal to 0. So when we do the derivative, a 2 comes down, it kills the 1/2. So we would have sum of I equals 1 to n. We're going to get this xi minus mu prime over sigma I. And then we have to take the derivative of what's inside. When we take the mu prime derivative, we'll get a factor of minus 1 over sigma I. So we would pick up a minus 1 over sigma I. And that would be equal to 0. Okay, so let's break the sum up into 2 parts. So we would have a sum of our first term. The first term is going to have xi over sigma I squared, and I guess there'll be a minus sign. So we would have a minus xi over sigma I squared. And then the second term is going to be minus and minus, so it'll be a plus. The mu prime is a constant. It has no I index, so I can pull it outside. And then we're going to get 1 over sigma I squared. So it'd be sum of I equals 1 to n of 1 over sigma I squared. And that has to be 0. And so now we just solve for mu prime. Okay. So if I want to solve for mu prime, I'm going to take this term over to the other side. So we would have mu prime sum of I equals 1 to n 1 over sigma I squared is equal to sum of I equals 1 to n xi over sigma I squared. And the last thing we'll do to isolate mu prime is we'll just divide by the sum on the left. So let's divide by left hand side sum. And so our weighted mean is given by mu prime is equal to sum of I equals 1 to n of xi over sigma I squared divided by sum of I equals 1. I'll rewrite it with more space. Okay, so weighted mean mu prime is sum I equals 1 to n of xi over sigma I squared divided by the sum of I equals 1 to n of 1 over sigma I squared. So what I want to do is I want to see if this result has some of the features that we would expect from it. The first thing we could do is we could think about what would happen if all of the uncertainties were equal to each other. This is a weighted mean, but there's nothing saying that we couldn't apply this to a problem where all the uncertainties were equal. What it should do is we should recover the standard mean 1 over n times the sum of the individual measurements. Okay. So if all sigma I are equal, so that sigma I is just some constant sigma, then mu prime would be equal to, well, if all the sigma I are the same, they're constants, we can pull them outside the sum. So we'd have a 1 over sigma squared sum of xi. Then we'd have in the denominator 1 over sigma squared sum of I equals 1 to n of just 1. But of course, this sum will just be an n, 1 plus 1 plus 1 n times. The 1 over sigma I, the 1 over sigma squareds cancel. And so our mu prime would be 1 over n times the sum of I equals 1 to n xi. So this is as expected. Good. So the first thing we could say is that the mean that we calculated on Wednesday is just a special case of the more general weighted mean in this red box. Okay. The other thing we could do is we could check to see if this has the feature that we like or expect, that when we have terms where sigma I is small compared to others, it should be more important in determining the average. So let's do kind of a silly example. Okay, but a silly example, but one that maybe will demonstrate a point. Okay, so silly example. And so the silly example is going to be for x1, what we're going to measure is, let's say, I don't know, 1 plus or minus sigma. And then for x2, we'll measure 1 plus or minus sigma. x3 will measure 1 plus or minus sigma. Then we'll change it up a bit. We'll say x4 will be 2 plus or minus 2 sigma. x5 will be 2 plus or minus 2 sigma. And x6 will be 2 plus or minus 2 sigma. So if we took the average of these 6 measurements, neglecting the uncertainties, it would just be 1 plus 1 plus 1 is 3. 2 plus 2 plus 2 is 6. So the total is 9. 9 divided by 6 would be 1 and 3, 6. So 1.5. Okay, so a straight average, neglecting uncertainties, would give 1.5. Okay, so a normal average using 1 over n times the sum of the individual measurements would result in mu prime equals 1.5. We expect the weighted average to give a result that is closer to the values with small uncertainty. Okay, so another way of saying the same thing is that for these particular measurements, all of the measurements with x equal 1 have half the uncertainty as the x equals 2 measurements. So when we evaluate the weighted mean, we're going to hope that we get something that's closer to 1 than 2. So we should get a value that's bigger than 1, but less than 1.5. And so let's see what happens. Okay, so mu prime is, we'll just write out the weighted mean, xi over sigma I squared divided by 1 over sigma I squared. Okay, so for the first 3 terms, we get 1 over sigma squared plus 1 over sigma squared plus 1 over sigma squared in the numerator. And then for the last 3 terms, x's are 2. And then we have 2 sigma, and we have to square it. So we get 4 sigma squared plus 2 over 4 sigma squared. I got to get another one in there. Plus 2 over 4 sigma squared. And then down here, 1 over sigma squared, 1 over sigma squared, 1 over sigma squared, then 1 over 4 sigma squared, 1 over 4 sigma squared, 1 over 4 sigma squared. Okay. So first of all, every single term in the numerator and denominator has a sigma squared. I was going to cross them all out, but I think that'll be messy, so I won't do that. We could cancel all of the sigma squareds. And what we're going to get is 3. And then this is 1/2 plus 1/2 plus 1/2. So it's 3 halves. So it's 3 plus 3 halves in the numerator. And in the denominator, it's 3 plus, well, this time it'll be 1/4 plus 1/4 plus 1/4. So 3/4. And so let's see, what does that actually come out to be? 6. So it's, I think it's 9 halves. And then we have to 12 plus 3 is 15 over 4. Is that right? Let me know if I make a mistake. So I got 9 halves and 4/15, which is 18 over 15. I can divide by 3, I guess, 6 over 5. And so that is something that's pretty close to 1, but it's a little bit above 1. So as expected, our weighted mean is closer to 1 than the, I don't know, the standard mean of 1.5. Okay, good. So I guess this is, I mean, what is it? It's 1 1/5, right? So it must be 1.2. 1.2. Okay. Good. So that's the weighted mean. And we haven't yet done, how much time do we have? Where's my? Okay, good. We have 20 minutes. So what we haven't done is we haven't considered how to get the uncertainty in the weighted mean. And so that's going to be a little more effort, but it's not so bad. Okay, so to find the uncertainty in the weighted mean. So what should we do? What did we do on Wednesday? What are we going to use? Propagation of errors. Propagation of errors. That's exactly what we're going to do. So we know that, I'll write down the result one more time. So this is going to be the sum over I of xi over sigma I squared divided by the sum over 1 over sigma I squared. Okay, and propagation of errors says that sigma mu prime squared would be, let's see, the derivative of mu prime with respect to x1 times sigma 1 squared plus the derivative of mu prime with respect to x2 times sigma 2 all squared. And then you have to keep going all the way up to the nth measurement. Okay, so what we're going to try to do is we're going to try to take the derivative of this thing. So let's consider d by dxj. So j can be anything from 1 to n. And we're going to evaluate this derivative of mu prime. All right. So in our expression for mu prime, we only have x's in the numerator. Everything else, like the sigmas, are different for every measurement, but they're not x values. So they're constants with respect to this partial derivative that we're trying to do. So what we'll end up having to do is have the sum over I of d by dxj of xi over sigma I squared. And then the denominator is just a constant. Okay, I'll write this out in a little more detail. We'll do lots of steps here. So d mu prime dxj, what we're trying to do here. Well, I could do a little more manipulation here before I actually evaluate the derivative. This sigma I is a constant, so I can pull it outside the derivative. So we'll have in the numerator the sum over I of 1 over sigma I squared. And then we have the derivative of xi with respect to xj. And then we're going to divide by 1 over sigma I squared. The sum of that. Okay. So now we're going to have some fun. Okay. We will run into these kinds of derivatives all of the time. All right. Or let's say frequently in the remainder of the course. So let's consider dxi dxj. This is going to be equal to, well, there's a couple of cases. What if I and j are equal to each other? Like, let's say I is 6 and j is 6. What's this derivative going to be? 1. Okay, that's right. So for the case where I is equal to j, we're going to get a 1. what if I is 6 and j is 3? 0. Okay, so we would get 0 for I not equal to j. Does anyone, are you guys familiar with like a symbol for this kind of result? Kronecker delta, who's seen the Kronecker delta?
Oh, yeah.
A couple people, maybe you've all seen it, but you've blocked it out of your memory or something. So the Kronecker delta is our good friend, Kronecker delta. And it is the symbol delta ij. I'm not happy with my delta ij, and it has exactly the property that we just wrote down over there. So it is equal to 1 when the subscripts are equal to each other, and it's equal to 0 otherwise. So otherwise or I not equal to j are the same thing. Okay, so the reason that we're going to introduce this notation, like it seems silly, like if I could just write down the same expression, why do I need a new symbol for this? This, our friend here, is a killer of sums, and that's why we love him so much. Okay, so we will use the Kronecker delta as a sum killer. And I'll show you what I mean. Okay, so if we go back up to the top here, we have the sum in the numerator. And so I'll just write it down exactly like it is. So we have the sum from I equals 1 to n. There was a 1 over sigma I squared, and then we have a dxi dxj. And so we just said that we could represent that derivative as delta ij. Okay, so how is this going to be a killer of the sum? All I'm going to do is I'm just going to write out a bunch of terms of this sum. Okay, so there's going to be like the first term is I equals 1. So we get 1 over sigma 1 squared delta 1 j plus 1 over sigma 2 squared delta 2 j. And then we keep going, and then we'll end up at a special case where like this is I equals 1, I equals 2, I equals 3. Eventually, we'll get to I equals j. So when we do that, we'll have a 1 over sigma j squared delta I is equal to j, so we'll have jj. So this is the I equals j term, and that's the special one. And then there'll be some more terms, and then we'll get to like the last one, 1 over sigma n squared. This is I equals n delta n j. So if this is the I equals j term, all of these other ones are I not equal to j. And so all of these Kronecker deltas are 0. And then we have only one where we're going to get a 1. And so we have these n terms, but n minus 1 of them are all 0 because of this delta function, Kronecker delta. And so the sum I equals 1 to n of 1 over sigma I squared dxi dxj ends up being just 1 over sigma j squared. And so there is the death of a sum. And we should rejoice in that because it's going to simplify things for us a lot. Okay, so the rule of thumb is that if you ever have any sum that is of the form, so for any sum of the form, I don't know, it would be like something like I equals 1 to n of let's say some function of xi maybe. Okay, let's say some function of yi. Or, yeah, okay, yi. And then you have a dxi, dxj. This thing is our delta function, and what it does is it selects only the I equals j term from the sum. So this selects the I equals j term from the sum. And so what you end up with is just whatever f is evaluated at I equals j. So in our case, this f of yi was 1 over sigma I squared, and that just became a 1 over sigma j squared. Okay, so I know maybe it's a little bit abstract at the beginning, but once you get used to using it, it simplifies things a lot for us. So now this all started because we were just trying to evaluate this derivative of mu prime. Now we know that the numerator is just 1 over sigma j squared. The denominator doesn't change. Okay, so let's call this equation star, and then we'll go back to equation star. So returning to star, we have then the derivative of mu prime with respect to xj is what we were evaluating. And we decided that the numerator now is just 1 over sigma j squared. The sum is gone. And the denominator, we still have 1 over sigma I squared, where I equals 1 to n. Okay, now we have to put that into our propagation of errors. And so let's just remind ourselves what we were doing. We have now this derivative evaluated, and we just have to multiply it by this sigma I, so sigma 1 or 2 or 3 or 4, so on. Okay, so then we would say sigma mu prime squared. How are we doing time-wise? 10 minutes, good. Okay. So there is going to be the I equals 1 term. Now we just have to be careful because we're going to keep this at sigma j, and we're going to keep this, so sorry, we're taking a derivative with respect to xj, right? So it's actually the j equals 1 term. It's the first one we're going to do, and so this will become 1 over sigma 1 squared. So for the first term, we get 1 over sigma 1 squared, and then we have the sum of 1 over sigma I squared. That's the derivative, just 1 sec, and then we have to multiply by sigma 1, and then we have to square it, and then we'll get the next term. Yeah.
That first, like the derivative you have up there, since it has 1 over sigma squared in the numerator, couldn't you just rewrite that term as a sum excluding j? Dividing by, it's just going to remove the j term from that sum. It's the same thing.
Sorry, I don't follow.
So
what do you want to do?
Since you have, like, you can move that sigma squared j to the bottom.
Yeah, so I put it here.
Yeah, and that would cancel out from that sum the j term in the sum. So
Yeah, it would cancel that 1 term, but there would be n minus 1 terms that don't cancel.
yeah, so it's just the sum excluding that term.
Yeah, but we don't have a nice way to write. Well, it's not actually, because it's going to be something, we put sigma j here. Let's just pick a value, j equals 3, okay? Then we're going to get sigma 3 squared divided by sigma 1 squared plus sigma 3 squared divided by sigma 2 squared. Then the next term would be a 1. So it's some complicated thing, but yeah, you could in principle do that. I'm not going to, okay? So this is the first term in our propagation of errors. And then we have a term that is going to be the j equals 2 term. And then we have the sum we'll always have the same sum in the denominator. We have to square that. We get a whole bunch of other terms, and then we get the nth term, j equals n. So sum over I, 1 over sigma I squared. Okay. So you could probably see already that we could cancel some stuff a little bit. And so the other thing that we have is that every single term has the exact same denominator. So we could factor that out. So we would have sigma mu prime squared would be equal to, well, let's see. We're going to have 1 over the sum of 1 over sigma I squared. So that's the denominator, same for every single term. And then I forgot, they're all inside the square. So we have 2 of those, right? So we have to square that. And then what do we end up with? 1 over sigma 1 squared plus 1 over sigma 2 squared plus 1 over sigma 3 squared and so on. So this is 1 over sigma 1 squared plus 1 over sigma 2 squared plus 1 over sigma n squared. Okay, we get the square because we have 1 over sigma n, but it's inside the square. And so that's why it's squared. But this thing is just the sum of 1 over sigma I squared. Right? That's all it is. But that's the exact same thing that we have in the denominator here. We just have 2 of those in the denominator. So what we can do is we can cancel all of this with that square. And we say, therefore, our final result is sigma mu prime squared is equal to 1 over the sum of I equals 1 of 1 over sigma I squared. And that is our final result. This is the uncertainty in the weighted mean. Just one little note of caution. Sometimes students will like to say, oh, I have 1 over sigma squared in the denominator. I can just write that as sigma squared. That's not true. It's because this is inside the sum. 1 over a squared plus 1 over b squared plus 1 over c squared plus 1 over d squared and so on is not the same thing as a squared plus b squared plus c squared. So you just have to be careful about that. Let's do what we did with our weighted mean and say, okay, if all of the uncertainties are equal, do we get the result we expect? So if all sigma I are equal to, say, just sigma, right? So sigma 1 is equal to sigma 2 is equal to sigma 3. We just call all of that sigma. Then we would get sigma mu prime squared would be equal to 1 over, well, this would be the sum of I equals 1 to n over 1 over sigma squared. But now there's no index on the sigma, so it can be pulled outside the sum. And this is just 1 plus 1 n times. And so that's just an n. And so we get that sigma mu prime squared is equal to 1 over n over sigma squared. And now we could say that that's sigma squared over n, taking the square root of everything. Sigma mu prime would be equal to sigma over root n, which is the expected standard error. Okay, so again, just like we saw for the mean, the error in the mean reduces to the standard error when all the uncertainties are equal, or another way of putting it, the regular mean and the standard error are just special cases of this more general weighted mean and the uncertainty in the weighted mean. Okay, with that, that's where I want to stop. So we'll summarize all of the key results next time. I guess it'll be Wednesday. And then what we'll start on Wednesday is what I consider to be the kind of the most important or most interesting topic in the course. And that is, if I have a set of data X, so I measure Y versus X, and I have a set of 12 data points or whatever, and suppose I plot those and they come out to be like linear, they fall on a straight line. How do I determine the value of the best slope and the best intercept for the line to go through that data? And it's going to be another method of maximum likelihood type calculation. And our friends, the sum killer, the Kronecker delta, will make an important appearance in that analysis. All right, good. Thanks very much. Yes.
So